everyone, and welcome. Today, we are diving deep into one of the most powerful and, frankly, fascinating processes on the planet, uranium enrichment. It's the absolute key to unlocking the incredible energy that's hidden deep inside the atom. So let's get right into it.
What you're looking at here is the very heart of nuclear power. It's a chain reaction, where just one tiny neutron kicks off this incredible cascade that releases a truly enormous amount of energy. But here's the thing. To control this reaction, you can't just grab any old chunk of uranium. Nope. You need a very specific and surprisingly rare ingredient.
And this brings us to what we could call the uranium conundrum. See, the uranium you pull out of the ground isn't quite ready to go off the shelf, so to speak. It's not ready to power a city. It has to be refined. It needs to be enriched. So what in the world is enrichment? Well, think of natural uranium as a mix of two different types, or isotopes. Enrichment is just the process of increasing the amount of the one we really want, the rare reactive type called U-235. But the real question is, just how rare is it? This is the number you've got to remember, 0.7%. That's it. In all the natural uranium mined on Earth, less than 1% of it is the U-235 we need to get that chain reaction going. The other 99.3% is a different kind, U-238. This incredible scarcity is exactly why enrichment is so important, and also what makes it so mind-bogglingly difficult.
So, how do you separate two things that are, for all intents and purposes, identical? I mean, it's a huge scientific puzzle, and the entire solution, believe it or not, comes down to a tiny, almost unnoticeable difference in their weight. Let's meet the uranium twins. See, they both have 92 protons, which is what makes them uranium in the first place. Chemically, they act exactly the same. But look closely. U-238 has 3 extra neutrons. That makes it just a tiny bit heavier than U-235. And that tiny, tiny difference in weight, that is the only thing we can use to tell them apart and separate.
Okay, so to take advantage of that little weight difference, scientists came up with a pretty ingenious solution. It's a multi-step process that takes solid uranium ore, turns it into a gas, spins it around at incredible speeds, and then finally turns it back into a solid. So the whole modern enrichment process really happens in 3 big stages. First, you have to turn the solid uranium into a gas. Second, you inject that gas into a machine called a centrifuge and spin it really, really fast. And third, because one spin just barely does anything, you have to repeat that process thousands of times in a massive chain of these machines, which is called a cascade. So, step 1, why a gas? The simple answer is that it's just way, way easier to separate things based on weight when they're in a gaseous state. To do this, chemists combine the uranium with fluorine, creating a compound called uranium hexafluoride, or UF6. The handy thing about UF6 is that it becomes a gas at a pretty low temperature, making it perfect for the job. And now for the main event. This UF6 gas gets pumped into these tall, skinny, spinning cylinders called centrifuges. And when I say spinning, I am not kidding. We're talking up to 70,000 revolutions per minute. That creates a force that's literally millions of times stronger than gravity. It's just wild. So what does all that force do? Well, just think of a salad spinner. You know, when you crank it, all the heavy water droplets get flung to the outside edge of the bowl, right? It's the same idea here. The immense spinning force pushes the UF6 molecules that have the slightly heavier U-238 atoms out against the walls of the cylinder. And you guessed it, if the heavy stuff gets thrown to the outside, the lighter stuff tends to hang out closer to the middle. So those UF6 molecules with the lighter U-235 atoms, they collect near the center of the centrifuge. From there, we can just siphon off that gas, which is now just a tiny bit more concentrated in U-235. But the key here is scale. I mean, one spin in a single centrifuge barely makes a dent in the concentration. So to get to the levels we actually need, you have to link thousands of these centrifuges together in a massive series. We call it a cascade. The slightly richer gas from one centrifuge gets fed directly into the next one and so on down the line. You know, this whole centrifuge method is actually the modern high-tech version. The very first way they did this was a process called gaseous diffusion, which basically forced the gas through thousands and thousands of microscopic filters. It worked, but oh my gosh, it used an absolutely insane amount of electricity. The modern gas centrifuge is so much more efficient, and it's the standard that's used all over the world today. Okay, so after our gas has passed through this huge cascade of centrifuges, we've got our enriched UF6 gas. But here's the problem. You can't build a fuel rod for a reactor out of gas, right? We need to turn it back into a solid metal. Believe it or not, this final step is pretty straightforward, chemically speaking. You just react the enriched UF6 gas with calcium. Calcium loves to bond with fluorine, so it just rips the fluorine atoms right off, leaving behind exactly what we wanted from the start. Pure, solid, enriched uranium metal, all ready to be manufactured into fuel. So after all that work, what do we actually have? Well, it turns out that the level of enrichment, the final percentage of U-235 you end up with, determines exactly what that uranium can be used for. This final concentration of U-235 creates what we call different grades of uranium, and each one has a very different job. It all starts with the natural stuff, which can then be processed into low-enriched uranium for reactors, or if you keep the process going much longer, it can become highly enriched material for weapons. Let's take a quick look. So just as a quick reminder, this is our starting line. Natural uranium with that tiny little sliver of U-235. It's just not concentrated enough to sustain a chain reaction in the types of reactors that power most of the world. Now, after you run the gas through the centrifuge cascade for a while, you get to this, low-enriched uranium, or LEU. Here, the U-235 concentration has been boosted up to somewhere between 3 and 5%. This is the sweet spot. This is the stuff that fuels the light water reactors that generate clean electricity for millions of people. But what if you don't stop there? If you keep that cascade process going, passing the gas through more and more and more centrifuges, you can eventually get here, highly enriched uranium, or HEU. Once you get to 90% or more U-235, the material is now suitable for making a nuclear weapon. And that really leaves us with a final, pretty powerful thought. The exact same fundamental technology, the same process of separating atoms based on a tiny difference in weight, can create clean, carbon-free energy to power a city, or it can create the fuel for a weapon of unimaginable destruction. It's an incredible testament to human ingenuity for sure. But it's also a constant reminder of the profound responsibility that comes right along with it.